Let's write the third Maclaurin polynomial for this function. F of x equals 2 over x plus 1. Let's just stop right there and not even read anything else because we're going to have to use that to figure out other stuff, but let's just get there first, okay? So step one, let's do it. F is 2 over x plus 1. That's going to come in handy if we write it this way. And we're going to need the third Maclaurin polynomial, so we need to go all the way up to the third derivative, and we're also going to need to figure out some other stuff. So let's just jump in. Quit talking about it and just do it. Negative 2x plus 1 to the negative 2. F double prime is positive 4x plus 1 to the negative 3, and then f triple prime is negative 12x plus 1 to the negative 4. Okay, the third Maclaurin polynomial, this is centered at 0 because it is a Maclaurin polynomial. Taylor polynomials aren't necessarily centered at 0. If they are, they will say so. But a Maclaurin polynomial is centered at 0. And here's the general format. Here goes. We're going to write it in blue. Hopefully this marker is good enough. I hope you're good enough. So my third Maclaurin polynomial is going to be a lot of unnecessary stuff I like to put at the beginning of it just because. It is going to be f of 0 times x to the 0 over 0 factorial. Okay, a lot of unnecessary stuff. I paused for a second there. My brain was spinning like, what should I write first? Plus f prime of 0 x to the 1 over 1 factorial. Again, lots of unnecessary stuff, lots of like dividing by 1. Well, big deal, you know? And then f double prime of 0, x squared over 2 factorial. And then f triple prime of 0 over, or x cubed, over 3 factorial. Okay, let's switch to a marker that you can actually see instead of that sad little thing. Switch back to this one, which is also running out of ink. So the third Taylor polynomial, centered at 0, which is a Maclaurin polynomial, hard for me to say, f of 0. If I plugged in 0 for f, so f of 0 would give me 2. Okay, f prime of 0, it's good to know, is going to give me negative 2. F double prime of 0 is going to give me 4. And trust me, like you plug in a 0, you get a 1. Doesn't matter what you raise 1 to, right? F triple prime of 0 is negative 12. Okay, let's keep going with this. So f of 0 would be 2. X to the 0 over 0 factorial, so it's just 2 plus. All right, f prime of 0, which is negative 2, so negative 2x to the 1 over 1 factorial. And then you can see the sun shining into the windows. And then f double prime of 0, which would be 4. So positive 4x squared over 2 factorial, which is 2. We'll reduce that in a minute. And then f triple prime, which is negative. Why did I put a plus? It is negative 12 x cubed over 3 factorial, which is 6. So let's go one more step on this. We'll take it over that way because we're going to need some board space here in a minute. And it's going to give me 2 minus 2x plus 2x squared minus 2x cubed. Lots of 2's. All right, we have just found the third degree Taylor polynomial centered at 0, or third Maclaurin polynomial. They may say third degree, they may say third. Either way, same idea. So now use your polynomial to find p of 3 equals negative 0.1. I'm going to go as calculator inactive as I can. This one's actually very doable without a calculator until we get to the actual value. Things get a little tricky there. It's doable, but not nice. P of 3, p sub 3, sorry, at negative 0.1 is, and we're going to plug it in. So 2 minus 2 times a negative. We'll go ahead and make that positive because, yeah, same thing, right? And then plus 2 times 0.1 squared. And then minus 2 times 0.1 cubed, negative 0.1 cubed. So negative here, negative from there is going to give me plus 2, 0.1 cubed. All right, let's figure out some stuff. This is 2. This is 0.02. oops, sorry, 0.2. This is 0.01 when you square it. 1/10 squared is 100th. So 1/100th times 2 is 2/100ths. You can see where this is going. 0.1 cubed, 1/10 cubed is 1/1000th. So therefore it is 0.002, which is 2.22222. How lovely. That's great. All right, well now we're going to compare it to the actual value. These are really great at approximating. In a minute I'll tell you a little bit more about why we do this. It's great. Well, I'll go ahead and tell you why we do it. We do it to simplify, I said this earlier, we do this to simplify our computations, just in case we don't have the computational power for it. And my mind is going back to a conversation I had with someone the other day. Yeah, let me get there in a second. All right, so let's find out the actual value, and we're going to compare it. So this is our approximation at negative 0.1, and then f of negative 0.1 is going to give me 2 divided by 0.9. I'll write that down. 2 divided by 0.9, which is totally doable by hand, but very not nice. So 2 divided by 0.9 is going to give me 2.222222222. So 2.2 repeating. This is so close to that, I can smell it. Great approximation. So the other day I had a conversation with an engineer, and we were talking, and I was like, I'm a math teacher, and he's like, I'm an engineer. And I said I teach calculus, and he's like, oh, well, I use Taylor polynomials. I'm like, yes, this is great. And so what he does is, I can't remember the exact title for what he does, but he basically uses Taylor polynomials to make approximations, because the chips that they put in the vehicles that they manufacture don't need to be super expensive, because it would raise the price of the vehicle. And so all the computations that a car or vehicle has to do in order to function properly can be done within a certain safety range with approximations. It's still perfectly safe, it's great, but you don't need that level of accuracy for the things that they're computing. If they used a level of accuracy that required super computational power, it would be a much more expensive chip that would go in there, and it would raise the price for the consumer. There you go. Thank you, Taylor and McLaurin. I'm thankful for that. Good stuff.